So let's move now to the examples part of our discussion of angular motion. We divide our discussion of examples into two parts to keep the videos short and simple. So first, let's look at the following problem. You have a toy top spinning with an initial speed of 1 radian per second. It makes a total of 30 turns before coming to a stop. Determine the acceleration of the toy. Now, the object here certainly has acceleration. As you can see, initially it has an angular speed of 1 radian per second, eventually coming to a stop. Final angular speed is 0. The angular speed, or in this case, the angular velocity changes. Therefore, the object has acceleration. Now, the question is, what type of accelerated motion is the object experiencing? Is the object undergoing uniformly accelerated, uniform angular acceleration that is? Or is the object experiencing non-uniform angular acceleration? If you look at the problem, there is no equation provided, no equation regarding the displacement, no equation regarding the angular velocity or regarding the angular acceleration, which means we have no equation to either integrate or differentiate. So that means, in all likelihood, this is uniform angular acceleration. With that said, you have 4 equations in the list to choose from for uniform angular acceleration. If you look at the third equation in the list, omega squared is equal to omega initial squared plus 2 alpha theta. And you look at the known values, you have initial angular speed 1 radian per second, final angular speed 0, and you have the angle traversed theta, 30 turns times the angle for 1 turn, 2 pi radians. You have 60 pi radians for the angle traversed. The only unknown value in the equation is angular acceleration. Plotting in the values, we are able to calculate the angular acceleration to be negative 2.6526 times 10 to the negative 3 power radians per second squared. The acceleration is negative, and we expect it to be negative because the velocity changed from 1 radian per second to a lower value, 0, which means the object is decelerating. Since the motion is positive direction, the acceleration should be in the opposite direction, which is the negative direction. So the acceleration that we calculate is negative. Moving on to the next example, consider the following problem. You have 2 rubber discs that are touching each other as shown in the figure, disc A and disc B, such that if disc A rotates, disc B will also rotate, but in the opposite direction. Starting from rest, disc A begins to spin and accelerate at a rate of 0.25 radians per second squared. Disc A has a radius of 0.5 meters, while disc B has a radius of 0.1 meter. What is the angular speed of disc B after 5 seconds? Since the two discs are connected together as shown in the figure, if one disc moves, the other disc will also move. But if one disk is at rest, the other disk will also be at rest, which means they both have the same time of travel, 5 seconds, and they both have the same initial angular speed, 0. Now, as the problem mentions, disk A has an acceleration of 0.25 radians per second squared. It is constant at this value. Therefore, disk A is experiencing uniform angular acceleration. Looking at the equation list for uniform angular acceleration, if we use the first equation, omega A is equal to omega A initial plus acceleration alpha A times time. The only unknown is the final angular velocity omega A, which we will calculate to be 1.25 radian per second. Now, you will recall from our discussion of angular kinematics, you will recall that angular velocity is equal to tangential velocity divided by the radius. Using this equation, we are able to get the equation for tangential speed. Thus, the final tangential speed for disk A, VA is equal to RA omega A. Similarly, we get the final tangential speed for disk B. VB is equal to RB omega B. For disks that are in contact, geometry tells us that the tangential speeds are equal. VA is equal to VB. Therefore, equating the two equations for VA and for VB, we are able to calculate the final angular speed of disk B after 5 seconds. 6.2500 radians per second. Next, we have the following example. A 0.5 kilogram sphere is attached to one end of a 0.2 kilogram rod, as shown in the figure. The sphere has a radius of 0.2 meter, while the rod has a length of 1 meter. You hold one end of the rod and spin it in a horizontal circle as shown in the figure. Determine the moment of inertia of the object. Now, let M1 be the mass of the sphere, 0.5 kilograms, and M2 be the mass of the rod, 0.2 kilograms. Let R be the radius of the sphere, 0.2 meters, and L be the length of the rod, 1 meter. Now, as you can see, the object is basically two objects connected together. You have the sphere connected to the rod. Each one has its own moment of inertia. Therefore, the total moment of inertia of the object is moment of inertia of the sphere, I1, plus moment of inertia of the rod, I2. Looking at the rod, the moment of inertia of the rod for axis of rotation at one end of the rod is 1/3 ml squared. You will recall that from the sample equations that we provided when we talked about moment of inertia. Now, suppose you forget that the equation for the rod with axis of rotation at one end of the rod is 1/3 ml squared. If you remember the equation for the rod with axis of rotation at the center of the rod, 1/12 ml squared, you can use the parallel axis theorem to determine the moment of inertia of the rod. Using the parallel axis theorem, you'll be able to derive that I2 is 1/3 M2L squared. and therefore you are able to calculate I2. Next, we look at the moment of inertia of the sphere. As you can see from the figure, the sphere is far from the axis of rotation. We can look at the sphere as an object moving in a circle of radius capital R, where capital R is equal to the radius of the sphere plus the length of the rod, 1.2 meters. You will recall that an object moving in a circle of radius r, the moment of inertia equation is mr squared. Therefore, the moment of inertia of the sphere for this problem is I1 is equal to m1 r squared. Knowing now the moment of inertia of the sphere I1 and moment of inertia of the rod I2, I total is equal to I1 plus I2, we get the moment of inertia of the object to be 0.787 kilogram meter squared. And that's it for part 1 of the examples discussion of angular motion.